Friends, welcome to my channel. Dhanesh here. I am going to discuss about qubit. The basis of quantum computing is the qubit. In quantum computing, a qubit or quantum bit, sometimes qubit, is the basic unit of quantum information. Unlike a normal computer bit, which can be 0 or 1, a qubit can be either of those or a superposition of both 0 and 1. We will discuss about some practical examples of qubit. One is spin of electron, which is angular momentum of an electron. The second one is polarization of photon. The spin of an electron, as I told, it's a type of angular momentum in which the two levels can be taken as spin up and spin down. The polarization of a single photon, in which the two states can be taken to be the vertical polarization and the horizontal polarization. In a classical system, a bit would have to be in one state or the other. However, quantum mechanics allows the qubit to be in a coherent superposition of both states simultaneously, a property which is fundamental to quantum mechanics and quantum computing. What is superposition? See, superposition and entanglement are two features of quantum physics on which these supercomputers are based. This empowers quantum computers to handle operations at speed exponentially higher than conventional computers and at much lesser energy consumption. Superposition refers to the quantum phenomenon where a quantum system can exist in multiple places or multiple states at the exact same time. In other words, something can be here, there, up and down at the same time. Comparison between bits and qubits. For a system of n components, a complete description of the state in classical physics requires only n bits, whereas in quantum physics it requires 2 raised to n complex numbers. A quantum computer consisting of n qubits can exist in a superposition of 2 raised to n states. If you add more bits to a regular computer, it can still only deal with one state at a time. But as you add qubits, the power of your quantum computer grows exponentially. We can say that if you have n qubits, you can simultaneously represent 2 raised to n states. I am going to discuss about quantum superposition. See, quantum mechanics is a fundamental theory in physics that describes the physical properties of nature at small scales of the order of atoms and subatomic particles. It's the foundation of all quantum physics, including quantum chemistry, quantum field theory, quantum technology, and quantum information science. Quantum superposition. See, quantum superposition is a fundamental principle of quantum mechanics. It states that, much like waves in classical physics, any two or more quantum states can be added together or superposed, and the result will be another valid quantum state, and conversely, that every quantum state can be represented as a sum of two or more other distinct states. Superposition refers to the quantum phenomenon where a quantum system can exist in multiple states or places at the exact same time. In other words, something can be here, there, up, down at the same time. Mathematically, quantum superposition refers to a property of solutions to the Schrodinger's wave equation. Since the Schrodinger equation is linear, any linear combination of solution will also be a solution. An example of a physically observable manifestation of the wave nature of quantum systems is the interference peaks from an electron beam in a double slit experiment. The pattern is very similar to the one obtained by diffraction of classical waves. The double slit experiment discovered that electrons and all quantum particles both exist as particles and probability waves. Quantum particles exist as probability waves means that we don't know for certain where these particles are. We can only know the probability of where they will be. In other words, particles can be here, there, up, down at the same time. In quantum realm, it's really magic. It's an illusion. Example is a quantum logical cubic state as used in quantum information processing, where which is a quantum superposition of the basic states 0 and 1. As you know, the basis of quantum computing is the qubit, unlike normal computer bit, which can be 0 or 1. A qubit can be either of those, a superposition of both 0 and 1. That's what it's shown in the figure. In the classical computing, you have 0 and 1. But in qubit, it's a superposition of both 0 and 1. I will discuss about the superposition and the Schrodinger's thought experiment. See, Schrodinger's cat is a thought experiment, sometimes described as a paradox, devised by, Austrian physicist Erwin Schrödinger in 1935 during the course of discussion with Albert Einstein. In Schrödinger's imaginary experiment, you place a cat in a box with a tiny bit of radioactive substance. When the radioactive substance decays, it triggers a Geiger counter, which causes a poison or explosion to be released that kills the cat. The cat ends up both dead and alive at the same time. Because the existence of a cat that is both dead and alive at the same time is absurd and does not happen in the real world. This thought experiment shows that wave function collapses are not just driven by conscious observation. Quantum superposition versus superposition of classical waves. You need to understand quantum superposition is fundamentally different from superposition of classical waves. A quantum computer consisting of n qubits can exist in a superposition of 2 raised to n states. In contrast, playing n musical sounds with all different frequencies can only give a superposition of n frequencies. Adding classical waves, wave scales linear, where the superposition of quantum states is exponential. That's why most of the optimization problems and we use quantum computers to solve most of the optimization problems and problems that grow exponentially. So That's all about quantum superposition. I am going to discuss about quantum entanglement. The theory behind quantum entanglement challenged the prevalent theories of physics and the beliefs of the most famous scientists. So I start off by sharing the quotes of Albert Einstein and Stephen Hawking, the most famous scientists of all time. Let's start. Let me discuss about Einstein's quote about the universe. This is the quote from Einstein. As I have said so many times, God doesn't play dice with the universe. This is the quote from Albert Einstein. This is the quote from Stephen Hawking. Not only does God play dice, but he sometimes throws them where they cannot be seen. So what is this quantum entanglement? Now I am going to discuss about the most weirdest phenomenon in science, quantum entanglement. After understanding quantum entanglement, you may think God may play dice with the universe. What is this uncanny phenomenon, quantum entanglement? See, quantum entanglement is a phenomenon observed at the quantum scale or atomic scale where entangled particles stay connected so that the actions performed on one of the particles affects the other, no matter the distance between two particles, even at a distance of light years. Next, I am going to discuss, we need to understand how we can create these entangled particles, how wave function and entangled particles are related. That's what I am going to discuss. So first, let me talk about wave function. See, wave function in quantum mechanics, a variable quantify or a variable quantity that mathematically describes the wave characteristics of a particle. The value of the wave function of a particle at a given point of space and time is related to the likelihood of the particles being there at the time. It is possible to separate two subatomic particles and both are described by a single wave function. These two particles are entangled. See, how do you create quantum entanglement? That's what I am going to discuss now. For that, this is the experiment, a simple experiment. We can, by using this simple experiment, we can create quantum entanglement. The vast majority of quantum entanglement experiments to date use photons as the entangled particles, for the simple reason that it's really easy to entangle the two photons. In these experiments, they put a bunch of calcium atoms into a highly excited energy level where the electron is forbidden to return to the ground state by emitting a single photon. The emission of one photon is followed within a few nanoseconds by the emission of the second. These two photons are entangled. So this is the way you can create entangled particles. Now, how spin is related to quantum entanglement? That's what I am going to discuss. In quantum mechanics and particle physics, spin is an intrinsic form of angular momentum carried by elementary particles. Spin is one of two types of angular momentum in quantum mechanics, the other being orbital angular momentum. By law of conservation of angular momentum, spin is conserved, spin is constant. Consider a parent particle It's shown in the figure with 0 spin, and let it decay into two particles. As discussed, spin is a conserved quantity and it can never change. If the parent particle has zero spin, then the two daughter particles must have opposite spin. So if one has a spin pointing left, the other one must be right. If one is up, the other must be down. Hence, when we add the two, we get 0, and hence the spin is conserved. The angular momentum is conserved. This is the simplest example of a pair of entangled particles, and they are governed by a single wave function. Next up, I am going to discuss about Einstein's spooky action at a distance. See, as long as the entangled particles don't interact with anything, you can separate the particles feet, miles, or even huge distances, and the two particles are connected by a single wave function, and they will have separate spin. As you know, the quantum world is intrinsically probabilistic. We can't predict the outcome of a measurement before we make it. It's really uncanny when we measure the spin direction of the both entangled particles. If the horizontal spin direction of one particle is left, then the spin direction of the other particle must be right. We can measure the spin direction of the two particles in quick succession very fast. We know that the fastest thing in this universe is light. 1 foot in 1 billionth of a second, or you know the speed of light is 3 into 10 raised to 8 meters second raised to -1. Let us assume that the two entangled particles are separated at 1 foot. After measurement, we understood that the quantum information can travel faster than light. Albert Einstein dismissed quantum entanglement as spooky action at a distance. Over the past few decades, however, physicists have demonstrated the reality of spooky action over ever greater distance, even from Earth to a satellite in space. The minimum speed of the entanglement is 1,44,500 times the speed of light. Next is I am going to discuss about BOHR-EINSTEIN debates. This was really important at that time. The BOHR-EINSTEIN, even now as well, the BOHR-EINSTEIN debates were a series of public disputes about quantum mechanics between Albert Einstein and Niels Bohr. Their debates are remembered because of their importance to the philosophy of science. Bohr proposed that entities such as electrons had only probabilities if they weren't observed. Einstein argued that they had independent reality, prompting his famous claim that God does not play with the universe. After understanding quantum entanglement, it is clear that God does play dice with the universe and sometimes throws them where they cannot be seen. Thanks for watching. Please like, share and subscribe. Thanks a lot.